The final part of our discussion about phase changes in Chapter 10 deals with something called phase diagrams. Phase diagrams depict the relationship of pressure and temperature and correlate it to which of the three standard traditional phases we can expect a particular material to occur. As the name implies, the triple point on a phase diagram is the one combination of pressure and temperature at which you could have either a solid or a liquid or a gas, or two out of the three at the same time, or all three at the same time. If you remember our discussion about the 32-degree plate of liquid water that contains an ice cube, that ice cube will remain in solid form indefinitely as long as there's no source of heat to make it melt. The liquid on the plate or platter will remain liquid at 32 degrees as well because it has no reason to freeze. There's nowhere to give its heat off to. It can't give the heat to the ice cube because the ice cube is at the same temperature, 32 degrees. So in that case, you have two phases occurring at the same time. At 32 degrees Fahrenheit or 0 degrees Celsius and 1 atmosphere of pressure, in other words, pretty traditional conditions, you can't have gaseous water at the same place and the same time that you have those other two phases. Keep in mind that just because all three phases can coexist, it doesn't mean that they do. Again, going back to our 0 degrees Celsius water sample, if my water is in the form of an ice cube, I just have the solid. Just because it can exist as a liquid at that temperature doesn't mean it necessarily does or has to. At the critical point, or above the critical point more correctly, the gas and liquid phases are indistinguishable from each other. In other words, the molecules have so much energy because it's above a certain critical temperature that they can't be squished into a liquid, and there's no physical difference between the liquid and the gas. All of this information is contained on something called a phase diagram. So this is a generic phase diagram for most materials. You can see on the left side, you've got the solid region, in the middle you've got the liquid, and on the right you've got gas. You should be able to pick out each of these regions on an unlabeled diagram. Remember that we're talking about pressure and temperature and what state each of these things exists in. For everyday materials, atmospheric pressure may be somewhere about here. Let's draw that in for now. We'll call this PATM, where ATM stands for atmospheric. That means the pressure that surrounds us on a daily basis. At atmospheric pressure, at a low enough temperature, for example, most things will solidify. Okay, we can pretend for sake of argument right now that this is water. This diagram is incorrect for water, and I'll tell you why in a minute. But the general discussion still works. At a low enough temperature, water is a solid. As you go to the right on the x-axis, of course, the temperature is increasing. So if we stay at atmospheric pressure, normal pressure that surrounds us, eventually an ice cube becomes warm enough that it gets to this line. This line represents the melting point. See how it's the dividing line between solid and liquid? If you warm up the ice cube enough, if it gets to a high enough temperature, it will get to the melting line. And as we described on the heating and cooling curve previously, it then starts turning into a liquid, and then eventually all of it becomes a liquid. And if we keep raising the temperature, you get a warmer and warmer liquid. And then look what happens. Eventually, you heat it up so much, it gets to this next line. This is the boiling line. This is the dividing line between a liquid and a gas. Once this material, in this case water, gets to this point, and we know that this point is a temperature of what? Do you remember what the boiling point of water is in Celsius? It's 100 degrees. So once water gets to 100 degrees, assuming we're at this normal condition of atmospheric pressure, it starts boiling and it becomes a gas. And then it starts heating up more and more as we raise the temperature. Now, some things, I'm going to erase this. So some materials, like carbon dioxide, this now becomes atmospheric pressure if this were CO2. So let's just make this notation here. Notice what happens as you heat up solid or dry ice, solid CO2. It gets to this line, but it doesn't become a liquid. It immediately goes into the gaseous state. Okay, this is what we call sublimation. Remember that vocab word, opposite of which is deposition. At atmospheric pressure, we are below this magic point called the triple point. And below the triple point, only those two phases are possible. So for the case of carbon dioxide, if you wanted liquid carbon dioxide, you would actually have to increase the pressure to a certain point, and I don't know off the top of my head what the critical pressure is, but you'd have to increase it to a certain point where the liquid could exist at some temperature. I have a tank of carbon dioxide in my house that I use for carbonating my beverages. And if you were to look on the pressure gauge, you'd see that the pressure gauge is up here someplace. And inside of that tank, I have liquid carbon dioxide. But you can't get liquid carbon dioxide at ordinary pressures, atmospheric pressure. This is, again, why we call it dry ice. It immediately goes, or not immediately, but directly goes from the solid state into the gaseous state, a process called sublimation. To get it to be liquid, you have to raise the temperature. Correction, you have to raise the pressure. Point B on this diagram corresponds to something called the critical point that we had on the previous panel. And the critical point is the pressure and temperature above which the gaseous and liquid phases are indistinguishable. So we should actually not have this line continuing here. Let's scribble that out. Anywhere up here is going to be basically a phase that is continuous. There's no boundary between the liquid like you see between the surface of a glass of water and the gas above it. So here's where you would have the critical temperature. And here's where you would have the critical pressure. Notice that anything to the left of this line, in other words, lower than the critical temperature, is still going to be identifiable as a liquid. Likewise, anything below this critical pressure down here will be identifiable as a gas. It's only when you get both above the critical pressure and above the critical temperature that you have this weird phase that you can't distinguish the gas and liquid. Can you figure out what line or curve AB represents? If you had to call this something, what would you call it? Well, look, it's the boundary between liquid and gas. When a liquid changes into a gas, we get vaporization or boiling. We could call this the boiling line. Likewise, we could call AC the sublimation curve or sublimation line, and then the point or the line from A to D, what would we call that? The melting or the freezing line. These are all vocabulary terms as well as terms that you need to be able to correlate to a given diagram. So if I were to give you a blank diagram, you should be able to tell me, for example, that the name of this line is the sublimation line. Or heck, I would even accept the opposite direction, deposition line. Now, I mentioned earlier that this diagram applies to most substances. Water, remember, is kind of weird. And what winds up happening basically is this. This section, the AD line, the melting line, for most substances has a positive slope. It goes up and to the right. For water, it would actually be going up and to the left. It kind of goes backwards. And that has to do with the fact that water behaves kind of weirdly when it freezes. Most materials get more dense, they get smaller, they occupy smaller space when they freeze, when they become solid. Water, of course, we know expands and becomes less dense. And that would be mirrored with the fact that the melting line goes up and to the left as opposed to up and to the right. But in general, the same ideas apply. Anything to the leftmost side here of the diagram is a solid. Anything up in this region, that would be a liquid and a gas.